The Tacoma Narrows Bridge tore itself apart on November 7, 1940, 4 months and 6 days after it opened. No one died, but that is almost the wrong fact to lead with. The right fact is this: the man who designed it had received a written warning before construction was finished that the deck was aerodynamically unstable. He read it, he responded, and he explained politely why the math said otherwise. The question this video exists to answer is not why the bridge moved. It is why a celebrated engineer, holding a warning in his hands, could not see what it meant. This is Fail Point. Tonight's report, Tacoma Narrows. By 1938, Leon Moisseiff was the most respected bridge engineer in the United States. He had contributed the deflection theory, later called elastic distribution, to the design of the Manhattan Bridge. The formula allowed engineers to build longer, flatter, more slender spans than anyone had thought structurally possible. It worked, repeatedly. The Golden Gate, the George Washington, Moisseiff had consulted on both. His calculations were not guesses. They were the foundation of a generation of American bridge engineering. That reputation is important because reputations decide which warnings get taken seriously. The state of Washington needed a bridge across the Tacoma Narrows in Puget Sound. The channel was 5,000 feet wide, and the winds through it were consistent and strong. Moisseiff won the commission in 1938. His design called for a deck only 39 feet wide, extraordinarily narrow for a span that long, with solid plate girders along the sides instead of the open trusses most long suspension bridges used. The plate girders gave the bridge its clean, modern silhouette. They also gave the wind nowhere to go. That detail would matter more than any other single decision made during the entire design process. Construction began in 1938. Almost immediately, workers noticed the deck moving. Not slightly, visibly, rhythmically, in rolling vertical waves that ran the length of the span. Local newspapers called it Galloping Gertie before the bridge even opened. The motion was documented. It was discussed. Engineers on the project installed hydraulic buffers to dampen it. They added tie-down cables from the deck to the floor of the straight. None of those measures stopped the movement. They reduced it enough that the bridge passed inspection and opened to traffic on July 1, 1940. The problem had not been solved. It had been made acceptable. In the spring of 1940, a man named Theodor von Karman read about the bridge's behavior. Von Karman was a Hungarian-American aerodynamicist at Caltech, one of the foremost experts on how air moves around solid objects. He understood something that structural engineers of that era generally did not. A solid-sided deck in a steady wind does not just push back against the air. It sheds the air in alternating vortices, organized swirls that peel off each side of the deck in rhythm. If that rhythm approaches the bridge's natural frequency, the structure begins to feed energy into its own motion. This was not a resonance problem in the simple sense. It was aerodynamic self-excitation. The bridge's own natural torsional frequency, its tendency to twist, was low. Dangerously low for a deck that narrow and that solid-sided. Think of it like a wine glass. Every glass has a pitch at which it will vibrate if you excite it correctly. A steady tone at exactly that pitch does not just make the glass hum, it can shatter it. The Tacoma Narrows deck was a wine glass, and the wind through the Narrows was capable of finding its note. Von Karman was not alone in recognizing this. Another engineer had already put that recognition in writing and sent it directly to Leon Moisseiff. The engineer was Ottmar Ammann, co-designer of the George Washington Bridge and one of the few men in America whose structural credentials matched Moisseiff's own. Ammann had written to Moisseiff expressing concern that the deck's solid plate girders would create aerodynamic instability under sustained wind. The exact contents of all correspondence remain partially in dispute among historians, but the substance is documented. The concern was raised in professional writing before the collapse. Moisseiff replied. His deflection theory showed the structure was adequate. The calculations did not flag instability. He trusted the calculations. That trust was not irrational. It had been right every time before. Here is the precise mechanism of Moisseiff's blindness. And it matters because it was not negligence. Elastic distribution theory was a static analysis tool. It calculated how loads distributed through a structure under weight, gravity, traffic, the steady push of wind treated as constant pressure. It was brilliant for what it measured. What it could not measure was dynamic behavior, how a structure responds to a force that changes in time, that oscillates, that finds a frequency. Aerodynamic flutter is dynamic. Vortex shedding is dynamic. Moisseiff's formula had no term for it. His calculations were not wrong. They were simply answering a different question than the one the wind was asking. November 7th, 1940. Wind speed, 42 miles per hour. Not a record, not a storm. A sustained, moderate wind entirely within the range the bridge was certified to withstand under static analysis. At approximately 10 in the morning, the bridge's motion shifted. It stopped undulating in vertical waves and began twisting, one edge of the deck rising while the other fell, the span rotating on its long axis. The torsional oscillation grew, not because the wind increased, because the deck's geometry was feeding energy back into the motion faster than any damping could remove it. The bridge was not being blown apart, it was winding itself up. At 11:02 a.m., a 600-foot section of the center span broke free and fell into Puget Sound. The only casualty was a dog named Tubby, left in a car by his owner who had fled on foot. The owner, a reporter named Leonard Coatsworth, had tried to return for the dog. The motion made it impossible. The Federal Works Agency launched an investigation almost immediately. The inquiry confirmed what von Karman and the aerodynamicists had already concluded. The failure was aerodynamic self-excitation, a phenomenon the design process had no standard method to evaluate. The static calculations had been performed correctly. That was the problem. The investigation, led in part by von Karman himself, produced something the engineering profession had not previously possessed: a formal framework for aerodynamic analysis of long-span bridges. Wind tunnel testing of deck cross-sections became standard practice. Open truss stiffening girders returned to bridge design. The replacement Tacoma Narrows Bridge, completed in 1950, used a truss deck 33 feet deeper than Moisseiff's original, open to the wind, not solid against it. Moisseiff did not see it built. He died in 1943, professionally ruined. His deflection theory was not discredited. It was simply understood at last to have limits. Every tool does. Leon Moisseiff was not a careless man. He was a careful man, using a precise tool in conditions that tool was not built for. The warning came from a peer. The math seemed to answer it. And a celebrated formula, exactly right for every previous bridge, became the reason he could not read the letter in his hands for what it was. Engineering failures rarely come from ignorance. They come from knowledge that has not yet learned its own boundaries. The Tacoma Narrows did not fail despite the best engineering of its era. It failed because of it. If you want the next report when it's filed, subscribe. Every failure has a point. Find it before it finds you.